Welcome to the deep dive. Today, we're tackling something really fascinating, how computers are basically learning to see and make sense of images.
hmm
And look, I know tech details can seem super complex, maybe even a bit like magic sometimes. But these systems, the large language models or LLMs that power chatbots, well, they're now getting surprisingly good with pictures too.
That's exactly right. We've all seen how amazing they've become with text, right? But now they're moving into the visual realm.
Yeah.
And the sources we looked at really dig into how that works and some of the honestly amazing things this tech can do now. We'll try to, to lay it out clearly without all the heavy jargon.
Okay, great. Because I want to understand this. How does a model built for words even begin to see a picture? I mean, it doesn't have eyes, obviously.
Right, no eyes. It's a totally different process. The first thing is what's called image encoding. Yeah. Basically, you take the picture and you convert it into a massive list of numbers. Think of it like a huge, complex spreadsheet where each number describes a tiny bit of the image, like the color or brightness of one specific dot.
So it's like translating the picture into a language the computer understands the language of numbers.
Precisely. That gets the visual info into a format the LLM can actually process.
And our sources mentioned convolutional neural networks, CNNs. What role do they play here?
CNNs. Yeah, they're a type of AI that's, well, historically been really good at image stuff. They act like little pattern detectors.
Detectors.
hmm
Yeah.
They scan that big grid of numbers from the encoded image and look for basic stuff, edges, corners, simple shapes, textures. They help find the fundamental visual building blocks and all that data.
Okay, so the image becomes numbers. CNNs find the basic shapes in those numbers. But how does the LLM then figure out what's actually important? Like if it's a photo of my cat sleeping on a blue chair, how does it focus on the cat and not just, the background wall?
Good question. That involves something called feature extraction. After encoding, the model needs to pick out the significant bits, the objects, faces, text, whatever matters.
Right.
And this is where attention mechanisms come in. It's a bit like how your own brain tunes out background noise to focus on a conversation. These mechanisms help the model weigh certain parts of the encoded image data more heavily.
So it's like a digital spotlight the LLM can use to highlight the key parts of the number picture.
Exactly. It learns what's likely relevant. And that ties into another concept mentioned, cross-modality learning. Sounds technical, but the idea is pretty straightforward.
Okay, lay it on me. Cross-modality.
It just means the LLM learns to connect different types of information like images and text. It's trained on huge data sets of pictures that also have text captions describing them.
Millions of photos with descriptions.
Yep. And over time, it starts to see the patterns. It learns to associate, say, the visual features of a dog furry texture, pointy ears, wagging tail with the word dog. It builds a bridge between the visual data and the language data.
Okay, so it's learning by example, connecting what things look like with the words we use for them. Makes sense. Now, one of our sources brought up vision transformers, or VITs. How do they differ from the CNN approach?
Right, VITs. They offer a different angle. Instead of CNNs scanning for local patterns like edges first, VITs do something interesting. They chop the image up into a grid of smaller patches, almost like puzzle pieces.
Puzzle pieces, okay.
Yeah, and each patch is treated like a piece of data, sort of like how an LLM treats words in a sentence.
So it looks at these little chunks first. What's the advantage of doing that?
The big idea is that the VIT can then learn the relationships between all these patches across the entire image right from the start. It's designed to grasp the overall context and how different parts connect, which can be really powerful for understanding complex scenes.
Interesting contrast. CNNs build up from small details. VITs look at how all the pieces fit together globally. Got it. Okay, let's move on to these multimodal models. CLIP was mentioned quite a bit. What's the deal there?
CLIP is a really big step. It stands for Contrastive Language Image Pre-training. Think of it, as one source put it, like a sophisticated translator between the language of images and the language of text.
A translator. How does it work? It mentioned a dual encoder setup.
Exactly. CLIP has two main parts working in parallel. One part, an encoder, looks at an image and creates a numerical summary, a representation of it. Another encoder does the same thing for a piece of text, like a caption.
Okay, two summaries. Then what?
Then, during training, CLIP's goal is to make the summary for an image very similar to the summary for its correct caption, and very different from the summaries of incorrect captions. It learns to match them up.
So it learns which text goes with which picture by comparing these summaries And what about learning through contrasts?
That's key to why it works so well. It doesn't just learn the positive matches, this picture goes with this text. It also learns from the negative examples. This picture doesn't go with that text. By seeing both what fits and what doesn't, it gets much more precise at understanding the relationship.
Like learning not just what a cat is, but also what isn't a cat, helps define cat better.
Exactly. That contrastive approach makes its understanding much sharper.
Okay, so we've covered how they see encoding, finding features, linking words and images via things like VITs and CLIP. Now, what can they actually do? What are the practical applications?
Oh, plenty already. One big one is image captioning. The model looks at a picture and generates a text description. A golden retriever catching a frisbee in a park.
That's super useful for organizing photos, like you said, or for accessibility.
Absolutely. Huge databases of images can be tagged automatically. Then there's visual question answering, or VQA.
VQA.
Yeah. You show the model an image and ask a question about it. What color is the car? Or how many people are in the boat? And it analyzes the image to answer.
Wow, that's more than just description. That's like reasoning about the picture.
It definitely involves a level of understanding. Another cool area is image-based search. Instead of typing keywords, you could upload a photo, maybe of a chair you like, and find similar chairs online.
Okay, searching with pictures. I can see that being handy. What else?
And content moderation. Platforms can use these models to automatically scan uploaded images for potentially harmful or inappropriate content, which is a huge task to do manually.
Right, helping keep things safer online. So, lots of current uses. What about the future? Where is this heading?
It's moving fast. Sources point towards better multimodal models that understand more nuance, like 3D shapes, depth perception in a 2D image, maybe even inferring emotions from facial expressions or scenes.
Getting closer to how humans perceive things. And speed.
Speed is crucial. As hardware improves, expect real-time image interpretation. Think augmented reality glasses instantly identifying objects, or self-driving cars understanding their complex surroundings on the fly.
That real-time capability feels like a game changer for things like autonomous systems.
For sure. And there's also this idea of cross-domain learning. Using the knowledge LLMs have gained from text about concepts, relationships, logic to boost their ability to understand visual information. Combining strength could lead to AI capabilities we haven't even thought of yet.
Okay, this is all making sense. But then one of the sources, that MIT research, dropped a real bombshell. LLMs trained only on text can somehow understand the visual world without ever seeing an actual image. How on earth does that work?
Yeah, that finding is pretty mind-bending, isn't it? It turns out that the sheer volume of text these models process contains a surprising amount of visual information, just described in words or, interestingly, in code.
So just by reading descriptions like a round red ball or
Yeah.
seeing HTML code that defines a blue square, the LLM builds some kind of an internal visual concept.
It seems so. The MIT researchers tested this. They prompted text-only LLMs to generate code-like instructions for a drawing program to create simple images, and they could.
What kind of images?
Things like drawing a row of bicycles, which shows an understanding of spatial arrangement, or a car-shaped cake, combining concepts, even a glowing light bulb, suggesting it understood visual effects described in text.
That's incredible. A language model essentially drawing based purely on text descriptions it's read.
Right. And then they took it a step further. They used these simple text-generated drawings to train a separate computer vision system.
Trained it on the LLM's drawings.
Yes. And that vision system, trained only on these basic code-generated images, could actually recognize objects in real photos surprisingly well. Better even than systems trained on some other types of synthetic images.
Well, that really highlights how much visual information is embedded in language itself.
Yeah.
The source also mentioned using LLMs to guide AI art tools.
Yeah, the idea there is AI art tools are great, but sometimes fiddly for specific edits. An LLM understanding your text command, like make the cat sit behind the chair, could generate a simple outline or code representing that change.
Like a blueprint for the art tool.
Exactly. A blueprint that guides the more powerful image generator to make the precise change you wanted, leveraging the LLM's language understanding.
Very clever. But wasn't there a catch? Something about LLMs being able to draw things they couldn't reliably recognize in photos.
Yes, that was a fascinating paradox. They might be able to generate code for, say, a fire hydrant based on text descriptions, but then fail to identify a real fire hydrant in a photo.
Why would that happen?
Likely because real-world objects have huge visual variation, different lighting, angles, styles. The LLM's text-based understanding might be more, well, conceptual or generic, not covering all those real-world messy detail.
Makes sense. Like knowing the idea of a chair versus recognizing every single weird chair design out there.
Nope.
But they also mentioned the LLMs showed creativity.
They did. When asked to draw the same concept multiple times, the LLMs often produced quite varied illustrations, different perspectives, styles, colors. It wasn't just spitting out one stored template.
Suggesting maybe some kind of internal mental imagery.
It certainly hints at something more flexible than just rote memorization. A kind of generative visual understanding derived purely from language. It's really profound stuff.
Absolutely. Okay, so that brings us to the final piece. Vision LLMs. These sound like the next evolution, specifically designed for this.
Exactly. Vision LLMs, or VLLMs, are models built from the ground up to process both images and text together in a deeply integrated way. Not just using text models to interpret images indirectly, but truly unifying vision and language processing.
So they're designed to think in both pictures and words simultaneously.
That's a good way to put it. They aim to reason about visual information more holistically, incorporating language context. Many build on that same transformer architecture we see in models like GPT, but adapted for multimodal input.
And what are their key capabilities? What makes them different?
They excel at understanding complex scenes, extracting text from images using OCR, but with contextual understanding, knowing what that text means in the image, and crucially, bridging vision and language, generating rich captions, answering complex visual questions, that sort of thing.
So a tighter integration. What are the main components inside a Vision LLM?
Generally, you've got a visual feature extraction module, maybe a CNN or a VIT to process the image into numbers. You have a language understanding module, like a standard LLM core. Then the critical part, multimodal fusion.
Fusion.
Yeah, where the image features and text features are combined and processed together. This often uses those attention mechanisms again, letting the model correlate parts of the image with parts of the text. And finally, task-specific heads for the desired output, like captioning or VQA.
Okay, so image processing, text processing, combine them, then generate the output. What's the high-level flow?
Pretty much that. Encode the image, encode any accompanying text, fuse those representations together, let the model reason across both, and then generate the final output based on the task.
And the sources mention specific techniques they use for image understanding.
Right. Things like scene recognition, is it a beach, an office, object detection, finding the cars, people, dogs, contextual analysis, understanding the relationships the person is walking the dog, and image-to-text generation, creating descriptions like CLI or BLAI do.
And for extracting text from images, how is it better than just standard OCR?
Because it adds understanding. It uses layout understanding for structure, knowing what's a heading, what's a table cell in a document. And semantic understanding, linking the text to the visual context, like reading 50% off on a price tag attached to a specific sweater in a photo. It's OCR plus context.
That context seems key. The applications listed were really broad.
For sure. Image understanding applications are huge.
Yeah.
Analyzing medical scans for anomalies, checking products in retail, interpreting surroundings for autonomous cars, and text extraction uses are everywhere too. Processing invoices, verifying ID cards, reading menus for visually impaired users, scanning checks.
And those specific model names came up again. CLIP, BLALP, Layout LM.
Yes, they represent different architectures excelling at different things. CLIP for image text matching and search. BLIP, often used for VQA and captioning. Layout LM and models like Donut are really specialized for understanding the structure and content of documents.
Building and deploying these seems like a major effort.
It is. It needs huge amounts of paired image text data, significant computing power for training, often leveraging pre-trained models, careful evaluation and optimization to make them usable in the real world.
So wrapping this all up, the big takeaway seems to be that LLMs are definitely not just about words anymore. They're getting incredibly sophisticated at navigating the visual world.
That's the core message. Through encoding, attention, contrastive learning, dedicated architectures like VITs, and now these integrated vision LMs, AI is rapidly learning to see and interpret images with increasing depth.
And it's fascinating that even without a PhD in AI, you can start to grasp the power here, how AI is bridging the gap between language and vision.
Absolutely. And it makes you think, doesn't it? How might this continued merging of visual and linguistic understanding in AI change things?
Yeah.
Consider how it could further blend our digital experiences with the physical world. What entirely new applications might pop up when AI can truly see, understand, and talk about the world around us as fluently as it handles text today? That's really something to ponder.